Okay, so when we are trying to find a maximum likelihood estimate, step one is going to be to find what's called the likelihood function. So the way, which is denoted with this L. So the way that we find this likelihood function, the likelihood function is saying what's the probability of getting the observed outcome. But we're going to express this probability as a function of the parameter that we don't know. So what we have over here is this is the probability of getting the observed sample that we got. Okay, and if we make this assumption that we're picking each of these x's from an identical distribution independent from each other, then the probability of getting the observed sample would just equal the product of each of the individual probabilities. So for example, I would want to calculate, well, what's the probability that the first x value I pick is x1? And that's exactly what this term is representing. Then we would multiply that, if they're picked independently, times the probability that the second x value is equal to whatever x2 is. And we would multiply all of them out, stopping with the very last observation that we get, which is that the nth one is equal to x sub n. All right, and so this likelihood function L, what we're calculating is what's the probability of getting the observed sample, and these calculations are going to depend on the value of theta. So the thing that you want to be careful about is when we use this notation, here what we have is that x is the kind of variable in the PDF function, and theta is some parameter in that function. But what we actually know here is not the value of theta. What we are given is the sample data, so given these x values. So when we write a likelihood function, we actually flip this around, and now what we know, what's given, are the values of x, and what's unknown is this parameter. So this likelihood function L is just a formula for the probability of the observed sample that we get by taking the product of each of these probabilities. And in the end, all of these things are going to depend on this parameter. So oftentimes we might just say that L is a function of theta. And now what we would like to do is then find the value of theta that maximizes that probability. But on this slide here, what I want to practice is how do we find formulas for the likelihood function? And then in the next slide, we'll practice how do we actually then maximize that likelihood. Okay, so for the first example, we have this sample of 4 observations, x1, 2, 3, and 4, that are now coming from a binomial distribution where we have 3 trials, and what we don't know is what's the probability of success in each of those trials. Okay, and so the binomial distribution, if we think back, it has a PDF that's going to depend on this parameter p, which is what's the probability of a success. We don't know what that is, but what we're going to do is say, well, given these 4 observations that we made, what's our best guess for what p is? And so for binomial distributions, we would say, how many successes do we have? And then multiply that by 1 minus p raised to the power of the number of failures that we have. So if we have 3 trials, if x of them are successes, then 3 minus x of them would be failures. Okay, so now the likelihood function here is going to be a function of this parameter p, given that x1 was equal to 1, x2 was equal to 3, x3 was also equal to 3, and the last one we got 2 successes out of the 3. And so to calculate this, we're just going to take f of 1, p, which is going to tell me how likely is it that we would get 1 success, times the probability that we would get exactly 3 successes was the second observation given P. Then the third observation was 3 successes again, and then the very last one we observed 2 out of the 3 trials were a success. So what I'm going to write is what's the probability of getting that sample, leaving P as some undetermined parameter. So for this one, we would say we have 1 success, so that's P to the first power times 1 minus P squared. We had 2 failures. And on this one, we had 3 successes. And I guess I don't need a term here, but I'll just put that as a placeholder to say we had 0 failures. Here we had 3 successes and 0 failures, and then the very last one we had 2 successes, so we're going to take P and square it and then multiply that by 1 minus P. And so if we group all of our terms together, then my likelihood function for P, let's see, I've got P raised to the 1, to the third, and to the second. So altogether, that gives us P raised to the 9th power. And then for all of the failures, the 1 minus P term, we would count up how many of those we have. And we have 2, 0, 0, 1. And we had 3 of those altogether. So we would have 1 minus P cubed. So that would be my likelihood function for this example. And then what's still left to do is then figure out, well, what value of P is going to give us the biggest likelihood, is going to maximize the function L. But we'll take a look at that next. If we wanted to find in the next example, what is the likelihood function for a sample of n observations that we make, and these all come from exponential distribution. Okay, so now an exponential distribution, just to remind ourselves, that's going to be a continuous random variable. But the way that we're going to find the likelihood function is going to be the same regardless of whether our random variable is discrete or continuous. So in part B, what we would want to do is say, well, this likelihood function, this is going to depend on this parameter. For exponential distributions, we usually use lambda, and what we're given is a set of observations. We'll keep them arbitrary here, x1 up to xn. And so this would equal the product of the PDF function evaluated each of those values. And so for an exponential function, the PDF is equal to lambda times e to the minus lambda x. So that means I would take lambda times e to the minus lambda x1 times lambda e to the minus lambda x2 all the way out to my last observation, which would be lambda e to the minus lambda times xn. And then we can group some of those terms together, and we can write out this likelihood function L of lambda. All of these x's would be given values, and the only unknown here would be lambda. So if we take this product out, we would have lambda raised to the nth power times e, say, to the minus lambda x1 minus lambda x2 minus lambda xn, which we could more elegantly write this as lambda to the nth power all times e to the minus lambda times the sum of all of the xi. So I could factor out a lambda from each of those terms and just write this as minus lambda times the sum of the xi's. So there is a general form for the likelihood function for this exponential distribution.